So we want today to look at implicit differentiation in a little bit more detail. When we started our calculus game, we thought of calculus in two big questions: what the slope of the line tangent to a curve at a given point, and what is the area under a curve and above an interval on the x-axis. And we answered those questions with the derivative for the slope thing and with the definite integral for the area thing. That's kind of the big picture of what's going on. Then we assign some meaning to these things, where the derivative is the instantaneous rate of change of y with respect to x when we write dy dx. And the area under the curve, that's integration, and integration is multiplication, but one of our factors is continuously variable. So the idea here is that we've got some kind of relationship between x and y, and we start when y is explicitly a function of x. So when we are able to write y equals f of x, we're writing y explicitly as a function of x. So here, y is an explicit function of x. The relationship between x and y is all the y on one side, just one y on one side, all the x on the other side. So for example, when we looked at y equals the square roots of 25 minus x squared, all we have on one side is the y. All we have on the other side is some expression involving x. Y is explicitly defined as some function of x. We could also have a relationship, an implicit relationship between x and y. So rather than using a function, rather than writing a function, we could have an implicit relationship between x and y. So we could have some function of x and y equal to some constants. So we have some expression where the x and y are all mixed together. Now we have an implicit relationship between x and y. Our favorite example of this is a circle. Functions are limited in that each input can correspond to only one output. That's the restriction of a function. Each input corresponds to one output. So the restriction on a function So if I ask what is f of -3, we can say 4. So with this explicitly defined function, when x is -3, f of -3 is 4. But in this implicit relationship, we know that if x is equal to -3, y can be 4 or -4. So here we don't necessarily have just each input corresponding to one output. Also, we don't have inputs and outputs. Everything is all jumbled together. So our strategy is still the same. Our plan is still the same. If I want to find the slope of the line tangent to a curve at a given point, I need to find dy dx. Dy dx is just the derivative version of slope. So derivative it's still the derivative. It's still dy dx, change in y divided by change in x. So the idea in implicit differentiation is that we're going to find dy dx even if the y's and x's are all mixed together in some fashion. And its implicit differentiation is based on the chain rule. So the machinery behind this implicit differentiation thing is the chain rule. This week is all about alternate descriptions of curves so things other than just functions. So the implicit differentiation is going to rely on the chain rule. So if we take an expression like y squared, I'm going to go y cubed. If I write the expression y cubed and then turn that into 3y squared, do the nx to the n minus 1 thing, that's the derivative with respect to y. So doing n times y to the n minus 1, this is the derivative with respect to y. So if we had to write one thing to make an equation and make it true, I'd have to say the derivative with respect to y of y cubed is 3y squared. So when we start applying derivative rules, we hadn't had to think about this so much up to this point. When we started applying derivative rules, everything was written in terms of functions. And instead of saying dy dx, we just said f prime of x because there was only one variable running around. And so f prime of x told you that x was the variable we are taking the derivative with respect to. That was a really clunky sentence. English sucks for the communication of math. So. But it's the only other language I have. So if we want to find the derivative with respect to x of an expression like y cubed, we start off with 3y squared. So if we want to find the derivative with respect to x of y cubed, we start off with 3y squared. That's the derivative with respect to y. And the chain rule says we can multiply by the derivative of y with respect to x. The derivative with respect to x, if there's going to be something in the middle, it's the derivative with respect to y times the derivative of y with respect to x. If there were two things in the middle, The derivative with respect to w would be the derivative with respect to y times the derivative of y with respect to x times the derivative of x with respect to w. If there were three things in the middle, I don't want to say it. So instead of just writing 3y squared, we say times dy dx. If I want the derivative with respect to y, I just say 3y squared. The derivative of y cubed with respect to x is 3y squared times dy dx using the chain rule. Take the derivative of the outside, leaving the inside alone, and multiply by the derivative of the inside. So this is not a new thing. This is the same chain rule what we had before. We're just looking at it differently. We're having to remember that there is an implicit relationship between y and x. Any questions? So that's what we're relying on. We're using the chain rule because the problem is set up with the understanding that there is a relationship between y and x. And I want to find the derivative in that relationship. I want to find dy dx. Any questions? Comments? Snide remarks? Everybody looks so stoked. The amount of stoked you are with the end of the semester looming is, I think, in proportion to the amount of dread you might feel with your final exam. I have to say final exam from now until the end of the semester every day, so you're less afraid of it. Like if all I did was like the week before the last week of class, the last day of class, be like, well, hey, I'll see you all on Wednesday for the final. I'd be like, oh, it's all scary. But if I just keep saying final exam, you'll all get used to it. Which is kind of a terrible strategy because we do that for other things. It's like, well, things that you might be afraid of. Let's just try to make you numb to those things so you don't see them anymore. But that might be a distinctly American problem. So here's what we want. We want to find the equation of a line tangent to a curve at a given point. But the new game that we're going to play starting this week is that the x and y will all be mixed together in some kind of equation. So when we have an expression with just y in it like this, we take the derivative, it's 3y squared. There was just one thing. So in another example, let's suppose that I've got x cubed. Oh, let's go x squared, because I want to use cubed for y. Let's suppose that this here I've got an equation in x and y, and the understanding is that x and y are related in some fashion. We're using this equation to make a relationship between x and y. We're not thinking of x and y as being independent variables. We're very much thinking of this as a curve. This is an equation that describes a relationship between x and y. So this equation is describing a relationship between x and y. So when we look at the x, we say that's the x, that's just a variable. That's the x of the dy dx that we're looking for. When we look at the y cubed, that has x in it. We want to see that y cubed and think that has some x in it. When we're thinking in terms of dy dx, We're thinking as x is being contained in this y. When we're looking for dy dx, the reason that we're looking for dy dx is that dy dx evaluated a point will tell us a slope at that point. So when we're looking for dy dx, view these y factors I want you to see that y cubed factor as having some x in it. So if 5x squared y cubed is equal to 40, I wanted to write it here. Oh, well, I want to find, take a minute and think about what we'll need to do to find dy dx. We know we're going to eventually use the chain rule because the derivative of y cubed with respect to x is 3y squared times dy dx. The derivative of x squared with respect to x is just 2x. But how are we going to put those together when they're combined in this fashion? Finally have practice test to read. So I haven't put the practice test 3 canvas one up. I discovered that this morning when I went to check how y'all were doing on the canvas portion of practice test 3. It's like, well, why has no one submitted it? Because I have not asked any questions yet. So sorry about that. I'm not sure I have a solution for that because I don't have a budget to hire someone to like do that end of the job. So we did the debrief on the test. Oh, good. I'm glad I recorded that. Okay, so we did the debrief on that test. These problems will show up on Canvas as the Canvas portion of the test. So you can fix anything what is broken. That's about it. That's all I have to say about that. I guess on the Canvas portion, there's not going to be one where you have to draw a graph. So I haven't found a good like thing that you could draw graphs inside. So. All right, so back to this problem. We were looking for dy dx, and I've got this mix of x and y. Now we have a few options. One of our options is to solve for y, keeping in mind that sometimes if we undo some functions aren't invertible. In this case, solving for y is a great option because y is being raised to the third power. All we would have to do is a cube root or a 1/3 power. And that is an invertible function. The only thing that's happening to y is an invertible function. So we don't have a lot to worry about here. So one option. And before we had the technology of implicit differentiation, that's the strategy we would have to employ. So solving for y. If we, depending on what we're doing. So it'll work mostly, it'll work since the function of y is invertible. That is, we can undo an odd power. The cube root of y will cancel out a cube of y. The reason I bring this up is that if we had like a y squared, like we had in the problem last week with the circle, when y with the function y squared, what's happening to y is not invertible. So we have to know that it's not invertible and know what the consequences of finding the square root of both sides are. So we have to know how to deal with this square root of both sides thing. We have to know that that makes a plus or minus. Similarly, if we had cosine of y somewhere in the problem, solving for y might not be possible because cosine is not an invertible function. Thinking back for more context, in a function, each input only corresponds to one output, but each output might correspond to several inputs. And that makes a function not invertible. So one strategy that we can employ here is to just solve for y. Y is the cube root of 40 over 5x squared. One of the things that we have to keep in mind, if we were looking for things like critical points, you have to remember critical points happen when the derivative is undefined. And in that case, the derivative of the function that we just proposed would be undefined at 0. And so that would be a critical point. But if we're just trying to find dy dx, we could do it that way. So it might write y is the cube root of 40 over 5x squared. So I could write y as 2 over x to the 2/3, or 2x to the 2/3, or x to the negative 2/3. We didn't have to do anything fancy because the inverse of a cube is a 1/3 power, or a cube root. So this raises the question, why would we do implicit differentiation if we could just find a function for y and then take the derivative normally? Because we can't always find a function for y, and it's not about finding the derivative. It's about understanding how these things are all related. All right, so we can also, rather than solving for y, we can just take the derivative of both sides with respect to x. So this will be solving for y and then finding the derivative. If we wanted to do implicit differentiation, we're just going to take the derivative with respect to x of both sides. Right side is easy. The derivative of 40 is 0. There's no x and y. On the left, I've got a constant 5. That's a constant factor. That's just going to carry along. But I have x squared, the derivative is 2x. And I have y cubed, the derivative is 3y squared times dy dx. But those two things are being multiplied. So I can't just take the derivative of each of the factors. The derivative of a product is not the product of the derivative. So what we're going to have to do here is turn the page, because that was bad planning on my part. So the derivative on the right, the derivative of 40, that's the derivative of a constant term. That's equal to 0. On the left, the derivative of the 5 times stuff, that's a constant factor. So 5 is a constant factor. So this would be 5 times the derivative with respect to x of x squared y cubed. The derivative of 40 with respect to x is 0, because 40 is a constant term. I also have the bad habit of saying things like the derivative of a constant is zero, but not if it's a constant factor. So we have to distinguish. The derivative of a constant term is zero. The derivative of a constant factor gets carried. What we want to remember is that the y cubed has some x in it. In fact, in the previous go with the problem, we specifically wrote down what x is contained in the y. So we have to look at the x squared times y cubed. Both of those factors contain x. We want to imagine both of those factors containing x. And since they are factors, when we want the derivative of factors, we have to use the product rule. We still have this 5 as a constant factor. But when we take the derivative of a product, we say take the derivative of the first. I spelled x wrong. Times the second. Plus the first. Times the derivative of the second. So we're looking at the first as x squared and the second as y cubed. When we write 3y squared, that's the derivative with respect to y, but we're looking for the derivative of y with respect to x. Now we have an equation that has dy dx, x, and y. The thing that we are looking for is dy dx. So that's what we're going to solve for. First, I'm going to divide both sides by 5 to get rid of that. And I've got 2x y cubed plus 3 x squared y squared times dy dx equals 0. As a note here, just divide by 5. Organize. The thing that we're looking for is dy dx. So when we're solving for a term, we're going to subtract anything that does, sorry, we're solving for a factor. Subtract any terms that don't contain that factor, divide by the coefficient of that factor. So I'm looking for the dy dx. So our strategy is to get the non-dy dx stuff away. So we'll subtract the non-dy dx terms, and then we'll divide by the coefficient, because we're still looking for dy dx. Now dy dx is being multiplied by a bunch of stuff. So we divide by the coefficient. Let's divide by the non-dy dx factors. That's not new. I haven't done calculus for a while. Once I finish writing the derivatives of both sides, even though I keep saying dy dx, that's just the thing that I'm looking for. We subtract the non-dy dx terms, divide by the non-dy dx factors. This is exactly the same thing you would have done if I asked you to solve the equation 2 plus 3t is equal to 0. You would subtract the non-t terms and then divide by the non-t factors. That's all we were doing over in that implicit differentiation. Subtract the non-t terms, divide by the non-t factors. It's just that our terms and factors had a lot more going on. Metaphor for modern life. Our terms and factors have a lot more going on. Now we can clean this up. We can clean this up because there's an x that we can cancel and there's some y's that we can cancel. So we could write this as, let's see, there'll be a y on top, 2y over 3x. Now, if we had a point, rather than plugging the x into the y, or x into the function to get the y, we would have a point, we would just plug both of those coordinates in, x and y. We do want to see if this is consistent with what we had before. So if you recall, we had written y as 2x to the negative 2/3. And if I replace the y in here with that expression, I'm going to bring the bottom one up instead of the up one down. So I got -2 times 2 is -4 divided by 3. X to the negative 2/3 divided by x is x to the negative 5/3, which is the same expression that we had before for dy dx. We're not doing different methods because one method is better than the other. I picked something that we could solve explicitly for y to see that both processes will are producing the same results. Any questions? How's everybody okay? This is just a different way of finding dy dx and the things that we have to remember when we're going about that. Tomorrow, we're going to have some practice problems. We'll be working at boards, finding equations of lines tangent to curves at given points. And instead of functions, we'll implicitly define the relationships between the x and the y. I guess unless you really are determined to write y as a function of x, then that's totally valid. How's everybody okay? All right, that's going to do it for today. I'll see you all on tomorrow, but have a good day and thanks for playing.